Hi, Madhukar.
Yeah, hi, sir.
So I'll make you, I'll
Yeah.
actually make you host. Okay.
Yeah, you can make me the host.
So which means you will not only have, it's already being recorded on live on YouTube. Okay.
Sure, sir. Sure.
What you have to do is actually before you leave the meeting, you have to make sure that you stop the live stream. Otherwise, it doesn't get stored. Okay. But in any case, I mean, I will also start recording as a backup.
Okay.
So you have to stop recording and stop live stream before you end the meeting. Yeah.
Okay, sure. So how do I stop?
Oh, now.
Okay, stop live stream. Yeah, sure.
No,
I can do that.
You have to do, since I made you a host.
Okay, how do I record? I can simply.
No. The record there's a record button.
Yeah. And the same button will be to stop the
cloud. I mean, you have to choose. Okay. Or what I can do is
I will make you the host or a co-host.
Yeah, you will have to make me a co-host. Then I can record, I think.
Yeah, so I made you a co-host.
Yeah, now I'll make you a host.
No, I'm still a host. I continue to be.
Okay, so because you made me only a co-host.
Yeah.
Okay. So you stop recording and then you leave the meeting. Yeah.
Yeah, certainly, sir. So I'll stop recording and I'll stop the live streaming.
If there's any issue that you'll have to do, then you have to send me, you message me. Yeah.
Yeah, certainly.
Okay. Thank you.
Yeah. Bye. Sure, sir. Thanks. Bye.
Video's off. Video is off. We can't see. Video is off. Delhi goes into lockdown.
Amay, we'll wait for a few minutes.
Yeah, sure.
Yeah, should we start or?
Yeah, I think you could start.
Yeah, okay, yeah, sure. So Diganta, I've made you a co-host just in case, there's some issue or something.
Sure, yeah.
Yeah, or if if Devajit joins later, then he'll have to be admitted.
Yeah, I'll take it.
Yeah. Can you see my screen?
Yeah, I can.
Okay. Yeah, so this is what we were looking at in the last class. We were trying to verify recurrent neural networks, and we were trying to use the idea of invariant inductive invariants, and yeah. So of course we had looked at some very simple toy networks, and the point that we were trying to, I mean, yeah, so one of the points that we made was that it's possible to verify recurrent neural networks just as you would verify feed forward neural networks. We have been saying that ReluPlex is a technique to do that. We have not looked at the technique yet, but we can assume that, and we have looked at some SAT based examples to verify feed forward neural network, something that Diganta had shown earlier in this course. So you can take a network, and I mean, one can imagine that if what is a network? A network is basically a bunch of neurons connected by edges with weights and biases. And what is happening really is some computation at each neuron, and these values are being propagated along these edges with some weights. And at every layer, you're doing some computation, and then you're propagating some values forward. Apart from the computation, what you're also doing is, depending on the activation function of every neuron, you try to apply that activation function on the computed value, and therefore that value may change to some other new value, and then the whole thing is being propagated forward, and everything, if you notice, everything is a formula, right? So you can pretty much write down the exact formula for your neural network in terms of your input, because it's these inputs are being multiplied by the edge weights, and then some big expression is generated, then some biases are added, and some activation function is applied. So basically, whatever is happening has a precise mathematical formulation, and therefore it's possible to give it to, if you're checking for a property, if you want to know whether can the output ever be something given the input is something, or given some pre and post conditions on inputs and outputs, you can check whether it is possible to get a satisfying solution using a SAT solver or an SMT solver, right? And that's what you had seen earlier in for this toy example that was shown. You had seen this, that it can be done. And even if you don't know any other way of verifying feed forward neural networks, you can at least go back to this thing. Whether it will scale or not is a different question, but at least you have a technique which can do this thing for you. It may not scale for large enough networks, or it may not scale in some cases, but there is a complete way of doing it. And so if you think in terms of that, at least these RNNs you can certainly unroll, and then you will have a feed forward neural network, and then you can once again capture all the computation that's happening in the network as logical formulas, and then you can ask questions about questions where given a precondition, will the post condition hold or not. So you can ask those questions, as you can pose these as satisfiability problems, and you can ask a solver to solve it for you. Okay, so this is something that we had looked at, but then we realized that this is perhaps not the best way of doing it, because verification of neural networks is exponential in the size of the network. So if you're unrolling it, that's you're really increasing the exponent in the complexity, which is not a good idea. So therefore, we don't want to unroll it. Now, if we don't want to unroll it, what is a way in which we can verify it? So this paper proposes one way of doing it. So we had looked at this very simple TWI example where you have these three neurons. There's an input neuron, there's a hidden layer neuron, and then there's an output thing, and the hidden layer has a memory unit corresponding to it. And we had seen that how this network behaves as different inputs arrive at different points in time. Okay. And then we had seen how a verification query, an RNN verification query looks like. So this RNN verification query, we saw that it has 4 components. There's a precondition component which tries to tell you some condition on the inputs. Then there is the network, of course, and then there is a post condition which is about the property that you are trying to verify. Okay, so if you're trying to, the post condition is typically the negation of the property that you're trying to verify. And these are the standard things that you'd see even in a software verification or a program verification framework. So you have a post condition, you have the network or the program, and you have a precondition. This is something that you additionally have here, which is the amount of time for which the property should hold, or the time for which we are doing the analysis. Okay, and this, of course, we spoke about. And the thing that we are interested in is circumventing this unrolling, because unrolling is not the best way of doing it. And this paper proposes a way to do it. So the construction is very simple. They say that you take your neurons that have a memory unit, and you convert these memory units into input layer neurons. So these memory units, no matter how deep they are sitting, you pull them to the input layer and you convert them as a neuron at the input layer. Okay, and you preserve these edge weights as they are going from the memory unit to the corresponding neuron. Okay, so these edge weights are preserved, and this is what you do. This is the construction that you do. This is the way you transform the network. And although it's not a feed forward network in the traditional sense, because in a feed forward neural network, you have edges that are only going from a layer to the very next layer. Here, because these memory units can be as deep as possible in the network, and you necessarily have to pull them to the first layer, then you can have arrows going to the third layer, fourth layer, and so on. So you can have these kind of arrows. So it's not, that's the only exception to this being a feed forward neural network. But okay, but anyway, it doesn't affect us as far as the analysis is concerned, or the verification is concerned, or the way we are going to think about it is concerned. Okay, so this is what you do. You pull out the memory neurons at the top layer, and memory units at the top layer, and make them as complete neurons. So these are now some things that will receive some input along with this, which was the original input. And you add one more neuron for the time. Okay, the time comes from the verification query. Remember that there's a time duration for which the property should hold. Okay, so after you've done this construction, you must, now that you've changed the RNN into a FFNN, except for these these edges going arbitrarily deep. So if now that you've changed the RNN into a feed forward neural network, you must also change the verification query. Earlier, your verification query had these 4 components: your precondition, your network, your post condition, and time. Now you should not worry about time, but have only these 3 things, which is your traditional verification query for a FFNN. Okay, so how do you do this? So the time thing, of course, goes away, but that's not very difficult to address, because you have added a neuron for time in your input layer. So your precondition, which normally talks about conditions on the input, can include this condition on the time. So this is what you see here. Okay, so this was your earlier precondition, that every input should be between -3 and 3. Now there is a condition on the time, and there are these other additional memory units which have been converted into neurons, and you must have some way of constraining them. Okay, so this is an additional expression that you need to constrain memory neurons. So this is something that we need. It's not clear how to get it, but we'll assume for now that this is something that we can get. Okay, the network of course gets transformed into this new network, so which is what we denote by n hat, and the post condition remains the same. Okay, so here we have tried to transform this into the RNN into a feed forward thing without doing the unrolling. Notice that you're losing some information, because earlier when this memory unit was sitting wherever it was sitting, there was an edge going from the memory unit to the neuron, and then there was an edge going from the neuron back to the memory unit, and this was helping us remember the exact value in these memory units at any point in time. Okay, now that you have pulled it back to the input layer, you only preserve this edge that feeds into the thing, but you don't try to remember what was being computed. Okay, so in that sense you're losing this information. So you can still if somehow you can capture what information should have been present here, then you can send this information to the neuron so that going ahead it does the computation in the right way, but there is no way of remembering what it was. Okay, which means that if the whole thing runs for some 5 time units, you cannot capture 5 different values here. Maybe these maybe the values were 5 4 3 2 1, so you cannot capture these 5 different values. Okay, because there is this one thing what you can capture, although, is an expression in terms of time which will give you 5 different values. Okay, so this is what is being tried here, that you have an expression in terms of the time. Okay, so for this memory unit, you say that at any point in time the value that it will have is something of this form, or is less than equal to this. Okay, so this is what you are really trying to capture here. Along with the time, you use this to capture what different values could have been fed into this neuron. Okay, except that we may lose precision here, because now we are earlier we could remember the exact value thanks to the edge that was feeding into the memory unit, but now since we have removed the edge feeding into the memory unit, we cannot remember it precisely. So therefore we are trying to approximate it with with some expression involving time and this, which we can do. But now, depending on how precise we have captured this relation, we will be able to get the behavior as accurately. If we have not been able to capture it very precisely, then we will not get an accurate behavior. Okay, and this is what roughly this is the discussion that we are having towards the end of the last lecture, that if we have over approximated the behavior, then we don't know, even if we have over approximated the behavior, and then if the property holds, then it's good. But if the property does not hold, then we'll try to find another invariant, and then it will not hold, then we'll try to find another invariant. And by invariant, I mean that this expression that has captured the value of these memory units. Okay, without realizing that this property may not hold at all. So this whole idea of trying to jump from one invariant to another, hoping that this time we'll be able to prove it, may not be very useful, right? So there is this notion of a refinement that one typically does when there is an abstraction and you're not able to establish the thing. Okay, so yeah, so I think, yeah, and then of course we had looked at inductive invariants, and why something is an invariant, and what are the conditions for some expression to be an inductive invariant. And the condition was something very simple. So the formula should hold true in the beginning, which is what we called as the initiation or init. And then we also wanted to satisfy consecution. Okay, which means that, if it holds true, and then if you do one body of the loop, then it should continue to hold true, which is the consecution thing. And then we wanted them to be strong enough. So we wanted them to be safe, so that, what you get is not a useless invariant, but it's also good enough to prove the property. Okay. So the other thing that we had done was we had looked at this RNN as a program. So you can really write down an RNN in terms of a program, and we had seen how this program is same as the RNN that we had looked at. And given now this program, you can talk about this notion of an inductive invariant. So here is a loop, and we want to find out an inductive invariant for this loop. So there are ways to find out inductive invariants. We are not interested in any of those ways at this point in time. Okay, but there is something that you can certainly do. Given this invariant, you can certainly check that it is an invariant. Okay, and you can do it in this program. If you model this problem, you can verify that this is an inductive invariant. Okay. So of course, this is in terms of program, but even in terms of neural networks, we wanted to do the same exercise. So given a neural network, we wanted to find out, find the invariants, and then we wanted to check whether they are actual invariants or not. And this, okay, so there is some relation between this finding and checking, right? So if you find something, if you're trying to find invariants, and if you have a good method of finding invariants, in the sense that this method will only give you actual inductive invariants, then you don't really need to check, right? So if your find method is good, you don't really need the check. But what this check allows you to do, if you have a check, which is typically easy for these things, so if you have a check, it gives you a way to find things more easily. For instance, if you have a method to check whether something is an inductive invariant or not, then instead of finding, what you can do is you can start guessing. Okay, so you can guess that, okay, let my invariant be, something, some x plus minus, ax plus minus by is less than equal to c. Maybe, you want to guess something like this, and you will pick some values for a, b, c, and you'll say that, okay, this is my inductive invariant. And it's possible, as long as it's possible to check whether something is an inductive invariant or not, you can have a way of, one way to find it is to actually guess it and then check it. Of course, if the guess fails, then you should be able to refine your guesses into more intelligent guesses and so on. But a guess and check is certainly a valid strategy for finding an inductive invariant. Okay, and this is where we had stopped last time. So if you have any questions, this would be a good point to ask them.
So like, how do we figure out the invariants? Is there other than guess and check?
So there are so there are ways in which there are different depending on so I've not looked at for neural networks, but for programs there are people have done some work in finding invariants by not doing. I mean, there are ways in which you can capture this problem as a.
No, I mean like specifically for RNNs. I mean.
Yeah, so for RNNs, it's not. So once again, if you really think about it, this RNN, as we have seen, it can be modeled as a program, right? And now
right.
You can find invariants for this program. So it's not really very different from a program, right? In fact, in that sense, a neural network is like a program. If you have RNNs, that means that you have a program with loops. So it's not very different from programs with loops, and you can pretty much apply any invariant generation technique that works for programs in here, except that if some of these techniques are dependent on the variables being integers, then then they may not be very readily applicable here, because of all the real values and the floating points and so on, right?
Right. It makes sense, I guess.
Yeah. Okay. Any other question? Okay. So, okay. So yeah, so we saw that, if we have a method of checking, then, instead of finding, we can do guessing. Okay. So let's look at a way of checking whether, okay, so we know that, somehow, we have seen this expression a couple of times. We know that, this V21M is less than equal to 3 times t minus 1 is being used as an invariant. Now, I don't know how they found it, but let's see whether it is, let's do the checking part first. Okay. So let me erase some of this and then. Okay. So if someone told you that, okay, here is an invariant, suppose you write you write a way to guess. Basically, you just take your bunch of variables, your V21 and TV11, whatever, if you just take your bunch of variables and you keep constructing expressions based on some grammar, you can say, I'll look at constant times variable, I'll look at variable plus variable, I'll look at variable minus variable, whatever. And you generate your terms, and then you use some operators, and you create some expressions. Now, suppose, there is a similar way of creating expressions that you have written down, and now you want to, sorry. Okay, I don't know how to. Yeah, I'm sorry, I'll have to erase once again. Yeah, so what I was saying is that, if you have written a method of guessing, then the guessing engine can keep supplying you, candidates one after another, and you can keep checking whether any of this is a suitable invariant or not, and we can. I mean, this gives you a way of finding something. So let's check whether, first of all, let's check whether this is an inductive invariant or not. Okay. And in terms of programs, I know that, you have done this, but, we can also pose this as a feed forward neural network verification exercise. Okay. So this checking can also be done on this network. Okay. So what does this really say? So remember that, if you have to check something, there are two parts to checking whether something is an inductive invariant. One is the init part, and one is the consecution part. Okay. So how do you check whether this holds true initially or not? Okay. So initially initially t is 1. Remember that, t was 1 in the beginning, right? So if t is 1 in the beginning, then this is what? This is 3 times 1 minus 1, which is 0. And then, v21m, v2 comma 1m should be less than equal to 0. And you knew that, this was the original network, and that, in the memory, you start with nothing in the memory. Okay. So this was 0 in the beginning. So for time is equal to 1, this is 0. And therefore, from this table, you can verify for yourself that, V21m is less than equal to 3 times t minus 1. Okay, so this holds true. So this is what initiation really means, that, you check that it holds in the initial state. So this passes certainly. Okay, so this is fine. Now we want to check whether the consecution holds or not, which means that, if it was true at the beginning of an arbitrary step, will it continue to hold true at the end of that step? So let's try to check this. So okay, so we know that, this V21m is less than equal to 3 times t minus 1. Okay, for some arbitrary t. So this is star. Okay, and this we know that, this lies between -3 and 3, because this has been given to us as a precondition. Okay, and what is it that we want to check? The post condition that we want to check is not the property post condition. This is for the verification part. Here we are checking whether consecution holds or not. So the post condition is that, you know, this is this the V21M, which is being which would have been sent here, is that the V21M in the next state is less than equal to 3 times t. Okay, this is what we want to check. Okay, so now this is not very difficult to see. You know, this is less than 3 times t minus 1, and this can be, you know, this. Okay, so this is what you want to check, that this is less than equal to 3 times t. Okay, when would this violate? When this would violate when it is bigger than 3 times t. Okay, when would it be bigger than 3 times t? When you're trying to send as big a value from here as possible. Okay, so let's send the biggest value here, the biggest possible value here, so which is 3. So you get 3 times t minus 1 from here, you get 3 from here, so you get less than equal to 3 times t at this point. And then there is ReLU that gets applied on this. So by application of ReLU, the value may decrease, but will certainly not increase. Okay, so this will continue to be less than 3 times t. Okay, and therefore you have proved that, you know, this is an inductive invariant. So you proved the initiation, you proved the consecution, and then you have proved that this is an inductive invariant. So what did we really do? You know, we really, what we did was, of course, init, you know, proving init is easy. Proving consecution is fine. You just take the same network, you just apply, you know, you just constrain these as, so your precondition, which was this for the original thing, now you are saying that, you know, V11 belongs to minus 3, 3, and V21M is less than equal to 3t minus 1. So your precondition becomes this, right? So you include this in your precondition. And then in this in this network, you add a post condition which says that, you know, this the output will be less than equal to 3 times t, and therefore you can again take the same network and you can ask this question, that is this possible that this is less than equal to 3 times t, and this lies between minus 3 and 3, but what you get here, okay, the final value here, it will not be on the output, because, you know, this is not relevant here. What comes in this memory is what gets computed here. So you want to verify that, you know, the value at this 2,1 will be less than equal to 3. So this becomes your post condition, this becomes your precondition, and we know that, you know, we can verify given a precondition and given a post condition and given a network, we can verify that whether the post condition holds or not. And this again can be done by either encoding it as a SAT formula, which you have seen, or by using specialized solvers like ReLUplex, which we have not seen, but we'll see. Okay, so what I'm trying to say here is that, look, you know, you had this problem of RNN verification, which you could have converted to FFNN verification by unrolling, but you didn't want to do that, so you converted it into feed forward neural network verification by looking for, you know, by looking for invariants. Okay, so this is what you want to do, but it's not clear how do you look for invariants, so you resorted to a guess and check technique. Okay, so guess and check method. Okay, so I'll tell you how the guessing works, and typically, you know, I've told you already, the guessing works by, you know, fixing a template and trying to generate expressions in that template and guess. And how does the checking work? So the checking has two parts: init, which is nothing, as in init means that, you know, just put that values in the expression and solve, and consecution, which can be posed again as a feed forward neural network verification problem, because there is a precondition, there is a post condition, and there's a network. So you can pose it as a feed forward neural network verification exercise. Okay, so this is something that you can do. And now when it, yeah, so I can, yeah, so at least in this paper, what they have done is, and this is all that I know about RNN verification using invariant generation, and I don't think there has been as in, yeah, I mean, then, yeah, I'm not sure, but as far as I have followed, I don't think there has been another work on trying to generate inductive invariants to verify RNNs. Okay, so in this particular paper, they say that they look for invariants of precisely this form, that the memory units can be alpha times t minus 1, basically alpha upper alpha lower times t minus 1. So they can be expressions of this kind, and then they try with different values of this thing to guess. So in fact, this works because this is the same thing, except that there is a 3 here in term. Okay, so they try different values of this, and these are very simple expressions. Of course, with a more complex RNN, you will need you may need a more complex expression, and it also depends on the kind of property that you're trying to verify. Here, it happens to work out because the property that you're trying to verify is that it never exceeds 16. It never exceeds 16, and therefore it kind of makes sense to have this kind of an invariant, because that the invariant is strong enough to discharge the property. But in general, you can find an invariant which may not be good enough to discharge the property, then you'll have to find another invariant, and then another invariant, and so on. Okay, which again comes back to this point that the fact that you have pulled this memory unit into this outer layer, you have lost the exact set of things that was being stored here, and now you are trying to regain it by using an expression of this form. So you have lost this information. Maybe there was the 5 different values that it had, and now you have lost this information, but you're trying to regain this information, but you cannot regain this information precisely. You can only gain it by allowing some expression of this relating to time, and maybe other variables, and some other constants or some operators, and whatever is allowed by your grammar. Okay, so you can try and regain that information, but you may not be able to gain it completely. So the kind of invariant that you need, it depends on how much information is really needed to establish the property that you are trying to establish. So this is the property that you're trying. Maybe I should change color so that. Okay, so this is the property that you're trying to establish. Okay, and you are trying to get an idea of what this memory thing is in terms of the time, so that you can actually approximate each one of these. If you have an expression in terms of time, then you can actually approximate each one of these and hope that you get a strong enough invariant that satisfies your property. But if you're not able to do that, there's nothing that you can do. Then you'll actually have to somehow get better invariants, more precise invariants. And I mean, you could also say that V21M is equal to star. That's also an invariant. Okay, V21M is equal to non-det. That's also an invariant, because if it is non-det, then it can be non-deterministically anything at the end of the loop. Okay, and but that's not. It's like saying true is an invariant for loops in any program, because true holds always, but that doesn't help you. Okay, so you can have it as imprecise as you want, but it will not be any good to prove the property. And you can have it very precise, but the more precise ones are difficult to guess. So you try and balance these two things. So you try to guess something which is slightly general, which means that something of this kind, instead of getting specific values, you try to guess something general. But this general should not be very general. It should still be strong enough to prove the property. And these ideas, or whatever I'm saying, it holds true. It doesn't matter whether you're doing in program verification or RNN verification. It holds true everywhere. Okay, so this is what this paper talks about. Okay, now of course there are some more details as to what happens in case of multiple memory units and what happens in case of, so if you have multiple memory units, let's say, if you are, just let me just erase some of it. Okay, so if you have multiple memory units, then you will have another, okay, so some v41, let's say m. Okay, so if you have another memory unit, you'll have another neuron in here, and then you'll have to find an inductive invariant in this also, maybe with respect to time. So in terms of programs, it's like, trying to find an inductive invariant, one expression which is in one variable, and then another expression which tries to capture what's going on with another variable, and so on. So you may have to find multiple expressions. You may have to guess multiple expressions. Okay, and if there are so there are multiple memory units in different layers, then there's also this question of what happens if there are multiple memory units in the same layer and all these things. So it's, these problems are very very directly related to what happens for programs when there are multiple loops or nested loops, and you have to find invariants in different variables and so on. So these problems are very common in both these things. This paper mostly just explores the idea of using an inductive invariant to prevent unrolling and still prove properties of RNNs. So this is therefore it talks about very preliminary a very preliminary template in which they try to generate invariants. Okay, so this is mostly presented at an idea level, and therefore it is at this level, but this can be tried with any RNN. How scalable the solution will be, or how easily you will be able to find an invariant or not, these are questions that remain to be answered. But as an idea, this can be tried anyway. Yeah. So if you, do you have any questions at this point? Am I?
None from me. None.
Okay. Okay. So Diganta, are you around?
Yeah, I think I can take over now. Yeah.
You will take over? Yeah. Okay. So Diganta will now explain, training of RNNs, and it will help you understand the project, or at least conceptualize these things better in terms of what needs to be done in the project. And then when I come back, maybe next class or whenever, I will talk about ReluPlex. I'll get into the details of ReluPlex. Yeah, sure, Diganta, over to you.
Okay, so yeah, just give me 1 sec. I'll get my pad.
Yeah. So most of this is an emerging area. So therefore, you will see many papers in this field in verifying DNNs and RNNs and other kind of networks also. CNNs also. They talk about an idea, and most of these are not in the most scalable format yet. But many of these ideas demonstrate how you can take this exercise up by borrowing ideas from program verification and techniques. The same techniques are applicable here also. So there are many such papers, and most of this literature is quite accessible if you are interested. So you can read up papers in this area. I mean, of course, if there isn't, most of these would be quite accessible because they will not talk about a very complex network, or they will not talk about very complex properties. Mostly these properties will be simple, and the networks will be simple, and it's about the applicability of the idea there. And slowly, as the field is emerging, of course, people are looking at more and more challenging benchmarks. And so therefore, in our project also, that's what we want to do. We want to start at the level of these ideas, and then we want to really see how we can extend them or how we can push them to be able to verify a decent sized network. So Digata, you'll be sharing the screen?
Yeah, I'll be sharing the screen.
Yeah.
Okay, so hopefully you can see my screen. I'll start there.
Yes, I can see.
Yeah. Yeah. Okay. So I'm going to briefly talk about RNNs, some of the kinds of RNNs that we are planning to look at in the project. So whenever I mention anything about the project, this is still slightly in the tentative stage, although you can start exploring along these lines if you want to keep ahead of it. But yeah, so we're going to in general look at RNNs, right? And I think Madhukar has already talked at length about like an overview of what RNNs are, so I'm not going to spend too much time on it. But I just wanted to give you maybe some more concrete real world use cases for things like RNNs, right? So RNNs are really useful for converting sequences to sequences. So you see, normal DNNs, they can take inputs of some fixed size, right? If you want to say label an image, then you can specify that your image is some say 100 by 100 pixels. So then you know that the input layer of your DNN is going to be 10,000. Sorry, I think there's an extra zero, but yeah. So DNNs in general can take inputs of some fixed size. But if you want to really work with sequences, then you need to modify your DNN architecture in some sense, right? Because you can't just have a DNN that will take an arbitrary long sequence as an input, because that won't work, right? So that's one reason why RNNs are used. And another reason is that RNNs, or in general, when we want to work with sequences, we often need to store some kind of context, some information or some encoding of what we have seen up until this point in the sequence. So that is another reason why RNNs are used, and this context is usually stored in this memory neuron of the RNN. So let's talk about some real world situations for an RNN to be used. So converting sequences to sequences, the two most common examples, actually one of the most common uses of RNNs is text processing, right? So for example, a chatbot that you can think of it as something that is converting sequences to sequences, right? It will take input, say you have your user has typed in some sentence, and the chatbot is going to get this sentence as input. This is a sequence of characters, right? And then it's going to produce its own string output, which is again going to be a sequence of characters. So the chatbot is converting sequences to sequences. So in this sense, you can have, say, an RNN based model that will convert your text query to text output. Another example with respect to text is, say, if you want to complete an incomplete text, which is something that we'll see in more detail later on. Say if you have, say, I have, and then it's blank. So this is an incomplete text sequence. You pass this to your RNN, and then the RNN produce maybe, say, I have 2 cats or something like that. It completes the text sequence into a sentence according to the kind of things it was trained on. So this is another example of taking something as an input and producing another sequence as an output, right? So the other, so the other use case for RNNs is for labeling sequences. For labeling sequences, one very good example, I think, which I didn't put in as a point over here, but I'll just write over here, is using basically labeling audio files, right? So if you think about an audio file, audio is just a sequence of samples, right? So audio is going to be a sequence of samples. So each sample is going to be, say, something between 0 and 1. 0 means, or even -1 and 1, depending upon what kind of a signal level is. So if you have an audio wave like this, so at regular intervals, you can take a sample, and each of these sample is going to be a value between 1 over here and -1 over here. I'm sorry, I'm drawing it up there very small. I hope that it's somewhat visible. Let me just bring it down here. Right, so you can imagine an audio file to be just a sequence of these samples. So an audio is also like an input sequence, right? So you may have something like, say, 0.7, 0.6, and then minus 0.2, and then so on, right? And then you can maybe take this audio file and label it as it being the voice of some particular person. Maybe it's a voice recognition program, right? So is it the voice of the owner of the house? If so, then open the door, otherwise don't. So things like that can be done. Yeah, so in all of these cases, you see the RNN needs to interpret the most recent thing that it saw in the sequence in terms of what it has already seen. So for example, if you're doing a text completion engine, then you may have already, or the most recent thing that you may have seen might be an R, right? So maybe you've seen an R, right? So if I tell you that you have seen an R and completed as something, then you can think of many different things to complete it. But, or let's say that you've seen an H. I think actually I've given H as an example over here. Sorry. So if you've just seen an H, and if I ask you to complete it as something, then you can complete it in many different ways, like maybe say HE for hello, or maybe HI or something like that. But you would not call this a good completion unless there has been a T before. So now suddenly, if you know that just before the H there was a T, then THR is a good completion because you can say throw, right? Or thrown. So if you have just seen an H, if H is your most current, say, member of your sequence, then depending upon what you've seen before it, what you want to complete it as, or what you want the next output of your output sequence to be, is going to change. So this blue prefix of the sequence, you cannot keep going over it over and over again, right? But what the RNN tries to do is it tries to store some summarization of the context that it has seen before in the memory neuron, which it will use to interpret the most recent input of the sequence and produce the output accordingly. So this is the, in general, this is the idea of an RNN. And of course, I think this diagram is probably very clear to all of you, that you can always fold an RNN or unroll an RNN into a large long DNN where you copy the recursive instance number of different times, right? So yeah, so any questions up until this point? I don't think this much. Okay, sure. So okay, so we're going to talk about some of the types of RNNs, right? So in general, when we say RNN, the RNN is usually refers to any neural network system where you have sort of a self loop or a loop or an edge coming in from the previous input, right? So anything that basically follows this sort of a structure. Anything that follows this sort of a structure can be thought of as an RNN, right? But as you can imagine, there can be many different ways of implementing this. So one can be your classic simple RNN, right? Where you just say you have the input of the current input coming in from the bottom, let's say. You have the previous value of your memory node coming in here. And then you have some DNN which combines these and produces an output and the next one, right? So in a simple RNN, in fact, this is usually just a single layered DNN. So what you have essentially is a one layered DNN over here. So let's just say it's a layer. So essentially then your output and the next value of your memory cell are both going to be just some weight times the previous value of your memory cell. So if I call this, say, m t minus 1 x t o t and mt, Then in a simple RNN, you're going to get this sort of a thing. So MT comma OT, this, if we think of this as a concatenated vector, this is just going to be some weights times MT minus 1 and some other weight times XT. And then this whole thing is going to be fed into some activation function, let's say E. Right, so this is usually your simple RNN sort of a structure. You just have a single layer, and here I think the diagram which Madhukar was drawing previously is going to be very directly useful, right? Because you can just pull this MT minus 1 as a node of, sorry, so MT minus 1 is going to be considered as an extra input, and then you are going to have XT over here. And then you just have this single layer over here. And then the output is going to be OT, right? And of course, we have this detached time thing that we had before. So this is the RNN structure that you've already seen. This is the simple RNN structure. But usually in practice, this simple RNN structure is, you can rarely train it very successfully on complicated data, in particular in form of for text processing sort of applications. The simple RNN doesn't seem to work very well. One of the reasons for that, intuitively at least, is that the memory here is very short term, right? So imagine if you are training it on, say, some source code. So one of the things that you would want to say, so you're generating a source completion engine, right? Something like GitHub Copilot, although GitHub Copilot is like much more complicated than any of these models. But one of the basic things that you would want such an engine to be able to do is that if you have some code that has, say, opened a brace, say it's some C code and it is opened a brace, and then there is, say, some statement here and you've left it here and you want it to complete, then at least it should close this brace, right? Or even if you don't want it to do it over multiple lines, if you, say, have something like X equal to this and you ask it to complete, at least if it completes the line, it should complete it with an ending brace and then put a semicolon here, right? But that is actually kind of difficult, right? Because imagine what's going to happen. Say the completion happens like this. So the first thing that it sees, the incomplete input sequence, is going to be initially something like this. And then as it slowly builds this complete sequence, so this entire sequence is a sequence of characters and it's being fed into the RNN. So if you think of the RNN as being unrolled, there is some initial hidden state, and then it's being fed for X, for equal to, for F, for O, and then for this again, right? And then it will start completing it. So maybe it says something like Y plus 1, right? So after this point, then so this Y plus 1 is actually the output that it was producing. So the text completion architecture will work like this. It will feed the previous output in as the input for the next iteration, right? So after this point, if it has seen all of this, and now if you wanted to, say, produce a closing bracket over here, right? If this is your desired behavior, that you want a closing brace over here, then in some sense it needs to remember this, right? And it needs to carry this information that it has seen an opening bracket across all of these 3 iterations. But for it to do that, what needs to happen is, okay. Can people hear me?
Yeah, sorry about that. I disconnected power.
I think Harsh also left at some point. Yeah, okay.
Yeah, Harsh has been disconnected for quite a while, I think.
Yeah, okay. Sure. But
Do you
yeah,
want to check with Harsh, Amay? Or?
Yeah, I'll just ask him.
Yeah.
Go.
yeah. Okay, sure. So yeah, so basically to carry forward this really old information that we've seen long back, that there was an open brace somewhere long back, it's going to be very difficult for the plain RNN to do, because for it to do that, this memory in each iteration is being completely changed by this layer, right? So if you imagine, say, if this memory was, say, 4 neurons, and let's say that this neuron having an output 1 means that we have seen an opening place, right? So then for this to be true, this 1 needs to hold through multiple iterations. So whatever the action of this layer is, it cannot change this 1. This output for MT also needs to have something like a 1 in the first place, right? And that needs to happen over and over again for as many iterations as there are between this opening bracket and where we want the closing bracket to appear. So to hold this information over for such a long time is going to be really difficult, because at each iterations you're in some sense changing the entire memory layer, right? So what you would need to have is something like M. So let's say that the application of this internal layer is capital F. Then capital F applied some large number of times, some n number of times on your old memory. So this one was M, so say MT, then this would be MT plus 1 plus 2 plus 3 and so on up until MT plus N. So MT plus N at, say, some ith position. The ith position was, say, the position where you want a 1 to appear if you want it to remember the fact that it has to put a closing brace. Then MT plus N at ith position should be the same as F applied on N MT at the ith position, right? So some property of on MT needs to remain invariant over multiple applications of this F. And as you can imagine, this is something that you can think of in terms of the verification angle, of course. Then you can think of, okay, is there some property that does remain invariant, and you can prove that your RNN does not satisfy that and so on. But if you think of it from the training perspective, it's very improbable that some complicated or some trained DNN layer with fairly arbitrary trained weights is going to actually have a property that it keeps some specific property of your memory unchanged over a large number of times, right? So in some sense, RNNs only have a very short-term memory, because after you've applied this layer some number of times, some 3-4 number of times. Yeah, are you back?
Yeah, really sorry about that.
No, it's, yeah, okay. My internet is also not very good today, so I'm also getting worried every now and then.
Many power cuts, very unusual here, but yeah.
Yes, basically what I was saying is that RNNs in some intuitive sense, RNNs tend to have a really short amount of memory, because if you keep applying this arbitrary DNN layer over and over, more and more of your memory is going to get scrambled up, and more information is going to get lost. So that is intuitively clear, I hope. Yeah. So the problem is having short-term memory for RNNs, right? So we have only short-term memory in RNNs. So the solution to that is this thing called an LSTM. So this stands for long short-term memory, where you basically add in some extra memory neurons to your RNN, which is going to hold a lot of memory over some long amount of time. So we'll look at what an LSTM is in more details a few slides down, few slides later on. But essentially, it's another variation of the RNN. And there's a diagram here, but I'll not go look at this in too much detail right now. There's a better diagram later on. Another solution to this, which is actually, it came about a little later than LSTM, but it's kind of like something between an LSTM and RNN. See, LSTM has got two things, right? LSTM has got a short-term memory and a long-term memory. So that doubles the number of hidden neurons that you need to carry around. So gated recurrent unit, or a GRU, this actually is something between an RNN and LSTM, which can go over, like get by using as only a single long-term memory without having any short-term memory at all. So there are variations of the standard, and there are many other variations as well. There are variations of the standard RNN model, which tries to deal with this problem of holding this memory over long periods of time. So yeah, some details about training RNNs. This works for any kinds of RNNs. By that I mean LSTMs, GRUs, everything of that. All of this is applicable for LSTM and GRU. So training data is going to be input and target sequences, right? So it doesn't depend on, it doesn't matter what you're trying to do. If you're trying to produce some output sequence from some input sequence, it's going to be some training input sequence and some target sequence, right? It could also be something like a input sequence and then target label, but that's also fine. So it's going to be input sequence and target sequence. And then what we do is we split the sequences into some n length chunks. N is like a hyperparameter over here. It's something like batch size when we deal with normal DNNs. But it's got some more significance to it. So we talk about some of the things that goes into choosing n. And then we unroll this RNN over these chunks. So if you unroll the RNN over the chunk, say O's are your target sequence. So this is your target, and this is your input. Then what we'll get is we'll get some DNN-like picture over here, right? So we get this sort of a DNN-like picture. And then we can train this unrolled thing like a normal DNN, right? So like a normal DNN, we can basically calculate the loss between the output and the target, and then minimize that and adjust the weights, right? But there's one like major difference. Actually, it's not a slight difference, but there's one difference between this and a normal DNN, which is that the various weights that appear in each one of these, right? So there's, say, some weight that appears here and some copy of the same weight that appears here. Note that these being copies of the same weights, these need to be fixed to be the same. So when we're going to train this, and sort of calculate the gradient of, say, of your loss between X and O, or actually not X and O, let's say O and some target. Then what you need to make sure is that, like, if you do it with a normal DNN like system, then what you would get is that you would get various different gradients for the different copies of the parameters over here, right? So HT minus 1 would have some set of parameters theta t minus 1, and you get a gradient with respect to that, a different gradient with respect to theta t, and different gradient with respect to theta t plus 1, and so on. But we don't want that. So we fix all of them to be the same, and we get a single gradient with respect to the entire like set of parameters for H, right? So that's what I mean when I say that we want to fix all of these to be the same. So when we do the backpropagation for this, we treat it as a normal DNN, but where we have added the extra constraints that the corresponding parameters in the various iterations of the RNN that we have produced, all of these corresponding parameters should remain the same. So in some sense, if you look at these W's over here, note that these W's are not indexed by some T, right? So that's what we're doing. We're making sure that W here and the W here and the W here are the same. So when we add those extra constraints, and that in terms of code or in terms of actually doing it in PyTorch would just mean that you use the same tensor variables for the various different iterations. So then when we add these constraints, then during backpropagation, those constraints will be kept in mind. And what you get when you do the gradient is you get a gradient with respect to a single W as opposed to a sequence of WTs, right? So then, you can adjust the W according to that. And so for each one of these chunks of input sequence, and you have a target output sequence, you do one training update and you change your W so that your output sequence is closer to the input sequence, right? And then you do this iteratively, just as we had done it with the normal DNN. So is this training picture clear?
Yeah.
Okay. So yeah, so basically you're going to fix all of these Ws and then get a single gradient and use that to do your gradient descent updates. And so you don't need to worry about really implementing this too much, because most of this is taken care of automatically by PyTorch. And we may or may not be giving you a train thing. So even if you have to do it, it's not very complicated, but you probably won't have to. Yeah, so one thing to take care of is that when we actually use the RNN, we don't unroll and use it. We actually keep this RNN in this form when we're using it, and we just pass the sequences and get the output. So we don't unroll it when we use the RNN. Yeah, so now one of the pitfalls, or one of the things that you need to keep in mind when you're doing this RNN training, is the problem of unstable gradients, essentially. So see, what's happening is that you have this. So if you consider this RNN black box as this some F, right? This is doing something like this, right? It's taking H and your weight W, and then it's producing so HT, and it's producing HT plus 1 and output, right? So you can think of your RNN as being this sort of an equation. So XT HT is going to be F applied on X. Sorry, OT HT is going to be X applied on HT, XT HT minus 1, and then W, right? So if you have, say, a sequence of some n length, then what happens is that as you talk about, say, this HT minus 1, and if you calculate the gradient of this entire thing, when you calculate the gradient, so this is your output, and you'll end up calculating the gradient with respect to this loss, right? So you have output T and then target T. So when you calculate the gradient, you'll have to calculate some derivatives of this function, right? And when you're calculating the derivative of this function with respect to W, you'll also have to calculate the derivative of this hidden state with respect to W. So this hidden state, you can expand it as something like this, right? XT, and then you can have XT minus 1, HT minus 2, W, right? And then when you calculate the derivative of this entire thing, so one part of the derivative of this with respect to W will come from here. Another part will come from this entire thing. And again, when you calculate the derivative of this respect to W, you can expand this inner H and you get a part from here. So in some sense, the derivative of this F with respect to W, if you try to calculate it, the derivative, or the W that you see inside here, will appear again and again for various different values of F, right? So what might end up happening is, imagine if your XTs and HTs and such are of some kind, so that the derivative of F with respect to this W is large, right? And then the derivative of this inner F with respect to this W is also large. And the derivative of the inner F coming from over here with respect to the W that you'll get over here, the derivative of this with respect to this W is also very large. So what you have is this nesting of Fs with very large derivatives with respect to Ws, right? So the more Fs you have nested like in this manner, and if the derivative of your each one of them is with respect to W is very large, then the final derivative that you will get is going to be very large, right? So if we sort of simplify some of those things, what we're calculating in some sense is beginning to look something like this, right? We're calculating the use black. We're calculating the derivative of or the gradient of something with respect to W, and then here inside here we have another F. So let's call this some underscore, and we expand this underscore to have another underscore inside an F, and we expand this to have some another underscore inside an F. And ultimately, if you keep expanding this, what you'll get is something like, so let's call this some other separate function F prime. This entire thing raised to the N, and each one of them depends on W, right? So your final gradient of your original this F that we had over here depends on many nested copies of the gradient of this function with respect to W, right? So if the gradient of this function with respect to W is something large, then you can imagine that this gradient is going to blow up. And this is actually a very common problem with RNNs, and this can lead to the gradient blowing up. In general, with RNNs, and very specifically with simple RNNs, this is a huge problem. And as you can imagine, is that if the gradient blows up, then depending upon what kind of activation functions you can have, it can send your weights either to something very large or something very small. And in either case, either things keep blowing up. So if you have ReLU, for example, and your weights end up becoming very large because of the gradient blowing up. So say your gradient of a particular weight is very large, and your weight ends up here, and the gradient stays large, and your weight just keeps increasing. So that can lead to a blow up. Or if you have something like, say something like this, then what can happen is that if once your weight gets pushed to some region over here, then the gradient becomes very small, right? And then the weight is stuck here. So your activation function in this case saturates. Similarly, both for ReLU and in this case, if your gradient blows up to some large negative value, then it can directly push your weight to some value in these regions, and it can lead to your activation function saturating again. So in general, what happens in a lot of cases that the gradients blows up, and then your activation function saturates, and then your gradient becomes 0, and then of course your training stops, and you're probably stuck in a bad spot in your training process. So this can happen very often. So this is one of the pitfalls that you need to be worried about when training RNNs. One of the ways in which you can sort of mitigate this is by engineering or trying values of N. So if N is too small, of course, your RNN never sees large sequences, and it never learns to keep contexts over a large amount of time. But if N is too large, then you run into the problem of your gradients actually blowing up. This especially hurts short-term memory systems more, because in short-term memory systems, this sort of recursive expansion happens more. You'll see that in LSTMs, because of the way that they're meant or that they're designed, the final value of the output, or let's say that the change in your long-term memory does not depend much on whatever you immediately saw, right? So what happens is that the gradient with respect to the long-term memory, the number of times your weights appear there, or the effect of weights appearing there again and again recursively, becomes much less. So with long-term memory, the changes are, or this issue of gradient blowing up is slightly more manageable. But usually the way you deal with it is by choosing your N as sufficiently small. If you of course, you can choose it. If you end up choosing it as very large, then you can think that you'll train over a large amount of long length chunks, and you'll get a lot of, you learn to keep a lot of context. But usually what happens is this gradient blow up problem. So this is the sort of balancing act that you'll have in terms of N. So small N means you don't learn context. But this gradient blow up happens for large N. So are there any questions?
No. Yeah.
So Diganta,
I think you should stop.
Yeah.
So yeah, I think this is a good place to stop. So I think we've talked some things about training these things.
Correct.
I had just one more slide with details of LSTMs, which maybe we can do next.
Correct. Yeah. So I think you can begin the next one with this, and then I can take over.
Yeah, sure. Yes. Okay.
Since we have only one guy attending, we should not extend it too much. This guy
Yeah.
this guy also stops coming.
No.
Yeah, sure. So I'll stop the recording.
Yeah, sure. So I'll also stop screen sharing. How do I do that though?
Even I am not clear how to stop the recording, but I'll press the record button again. No, that doesn't.
I think
no. I think it's only sir who can.
Yeah, stop the recording and the lights.
Stop